Okay, so let's move on with the next speaker. The next speaker is Ascoli. He's from Politecnico di Torino. So the title of his talk is How the Negative Differential Resistance of a Niobium Oxide Threshold Switch Enables to Induce the Fundamental Bifurcation of a High-Order Neuron in a Low-Dimensional Circuit. So please, Alon, the stage is yours.
Thank you very much for this very kind introduction. And thanks also to the organizers of this conference, because they did a really nice workshop. So good afternoon to everybody. So we can start the talk. First, I would like to acknowledge the people that were involved in this research, especially Professor Ronald Teslav from TU Dresden. That was my former affiliation. I was until last year. And then Professor Leon Chua from the University of California, Berkeley. Then we have Dr. Ahmed Samil Demirkol, which is also here from TU Dresden. Dr. Yanis Messaris and Dr. Vasilis Entinas, also from TU Dresden. And then my current colleagues, Professor Corinto and Professor Gili from Politecnico di Torino. And also, I would like to acknowledge, I don't know why the slide is not appearing, also our partners from NAMLab. I'm sorry that this slide is not coming, that are Professor Thomas Mikolajczyk, which is also professor from TU Dresden, and Dr. Stefan Slezacek, also from NAMLab. If you want to just remember something from this presentation, I will, since I always go very, I never finish my slide set, I better give you now the take-home message. So here, then we will go in details what it is, but maybe for some of you that know about the Hodgkin and Huxley neuron model, this is the famous bifurcation diagram from the Hodgkin and Huxley neuron model. And actually now we have, this is a fourth-order model, fourth-order dynamical system. It is a, we will go in the details about the equations, but we were able to design, or better, to use a standard cell, which is something that most of you have utilized in some form or the other. But we, through the theory, through bifurcation theory and local activity and edge of chaos theory, we were able actually to explore all the dynamics of this circuit, which is just a 3-element circuit. Here I will show you. This is a 3-element circuit. It has a capacitance, a memristor, which is locally active, and the current source, and we are actually able to qualitatively reproduce the bifurcation diagram of the Hodgkin and Huxley. So we dub this new circuit as the Hodgkin and Huxley neuristor. In fact, to the best of our knowledge, there is no other circuit that has ever been introduced with such a low complexity. It has 3 elements, and it is a second-order circuit, and is able to reproduce the cascade of bifurcations that you observe in the Hodgkin and Huxley neuron, which we will go through them later on. And actually, only theory could have allowed this, because actually, first of all, experimentally, it's very hard to detect, especially 2 of these bifurcations, the subcritical and the full cycle. It's very hard to detect them experimentally. And however, also, you have to tune the parameters in such a way to have this bifurcation diagram, because the dynamics are very rich. Despite the simplicity of the system, the dynamics are very rich, and this is enabled by the memristor dynamics. So if you don't set the parameters correctly, you can have other bifurcation diagrams. There is like 3 possible different bifurcation diagrams that you can have. So let us go now through some detail about biology. So Galvani, all too known enigma. So Galvani was an Italian scientist that in 1781 he was using a Leiter jar to charge, it was just a little bit charged, not so much. And however, it was able to contract the leg of the frog. But however, if a little bit was charged a little bit less, this was not able to. So this is the whole too known phenomenon, right? You just need a little bit, but it has to be above a certain threshold. And so this is the all too known enigma. So he was asking in his famous works, this commentary from 1791, how is it possible that such a tiny, so an electroscope could not detect this charge in the jar, but still, such a tiny electrical force was enough to contract the leg of the frog. So he was asking, is there some principle that we are not aware of that enables this to happen? And so we will see that basically this is an example of complexity, okay? And how to explain what are the necessary conditions for complexity to appear in a system, okay? Actually, Leon Chua has developed a theory. If you want to have details, you can look at the famous paper that he published in 2005 in the International Journal of Bifurcation and Chaos about the introduction of this physics principle that explain complexity in any physical system. In fact, this is actually the main statement of the local activity principle. So in order for complexity to emerge in a system, some of its elements must be endowed with the capability to act as local sources of energy under suitable polarization. And so there is a theory of local activity that has solid foundations, and it's based on quantitative methods to actually understand when a circuit can behave in a complex fashion. And so as an electronic engineer, you can also use this theory to tune the parameters of your circuit in such a way to guide the circuit to operate as you wish. So let us define local activity, and this is a definition that is applicable to any system, but since we are dealing with memristive systems, let us give the definition for a first-order memristor, the simplest case. Suppose that the memristor is current controlled, and first of all, we need to bias the device, right? Because nothing is for free, so in order to let it amplify the small signal, you first have to bias it. So you first insert a current bias, it's a DC current, into the memristor. You wait long enough that the transients have decayed to 0, and then you measure the voltage across the memristor and the state of the memristor, could be temperature, for example, in our memristor, at steady state. And then you superimpose the small signal around the operating point. So the operating point is basically the DC state, which is also unequivocally one-to-one corresponding to a point in the voltage current plane, which is usually the plane that engineers are used to look at, right? So P is our operating point, that is our bias point in the current voltage domain, which is unequivocally corresponding to one state, DC state, which is the Q, the operating point of the system. Then we superimpose the small signal current on top of the DC signal, and we, of course, measure then a total response from the memristor, which is there will be the DC component plus a small signal response in terms of voltage and in terms of state. And then we calculate the product between the small signal voltage response to the small signal current input. This is the local power, and we integrate the local power. So if you integrate the local power, you get the local energy, right? The net energy that has been absorbed by the memristor over the time from T0, when you apply the small signal, until a later time. Okay, if this integral ever goes negative, then you can basically conclude that the memristor is locally active around the operating point under which you have polarized it. So this is a strict and rigorous definition that Professor Chua introduced. However, it is not practical for testing purposes, and therefore, fortunately, he also introduced a theorem called theorem of local activity, which basically simplifies this testing investigation. And for that, one has to derive the small signal, the DC characteristic of the memristor, and the small signal model. So there are two tasks, preliminary tasks, in order to apply the local activity theorem, because the local activity theorem is applied to the local transfer function, which if it is a current control device, it's the small signal impedance. So suppose that we have done this task, we have concluded this task, then we can announce what the local activity theorem is. So basically, we need to test whether the memristor, which is current controlled in our example, is ever locally active, can it be ever locally active at some operating point. So you just take the small signal transfer function, which is in this case the small signal impedance, and you check basically the poles. If there is at least one pole on the right half plane, okay, so you can conclude that it is locally active. And then there are two marginal cases, okay, if there is a simple pole on the j omega axis and the residue is negative or a negative real or a complex number, and then if there are multiple poles on the j omega axis. These are not so frequent conditions, but the last one is very interesting because it has nothing to do with the stability, with pole location. It has to be checked whether the real part of the local transfer function, so z of s, but calculated at the Fourier frequency, is ever negative for at least one frequency, which could also be the DC. So could be also omega equal to 0. And that's why for memristors that are used in at our partners from NAMLab that have this S-shaped DC characteristic, one can conclude immediately from looking at this DC characteristic that they are locally active in the NdO region, in this negative differential resistance region where the slope is negative. And of course, if the slope is negative, then the fourth condition applies for omega equal to 0, right? Because the slope is actually the small signal resistance, which is the local impedance at omega equal to 0, which is real. It's real, of course, it's real, right? Okay, so what is about edge of chaos? Edge of chaos is basically it's a subdomain of local activity domain where typically the seat for complexity resides. So when you have a complexity in a system, typically it is poised near the edge of chaos. For example, when neurons are firing, Professor Leonchu has done a wonderful work on the Ascoli and Ascoli neuron, and he has demonstrated that when the neurons fire, they are poised near the edge of chaos. So what means edge of chaos? It means that it has to be locally active but stable, which means that the first three conditions do not apply, cannot apply. Only the fourth one. That's why I was giving emphasis to the fourth condition. Basically, all the poles are on the left half plane, but then the real part of the impedance, the local impedance, has to be negative for some frequency. Okay? This is the definition of edge of chaos, so it's quite simple. So basically, all physical systems can be divided into, okay, or better, they can operate as locally passive or locally active, okay? And there is a very small, the crown jewel region of the local activity is called edge of chaos. It's where all complex phenomena can appear. Okay, now let us go now into the details on the bifurcation diagram of the Ascoli and Ascoli neural model. So, of course, in the 1952, you're aware about Ascoli and Ascoli. They have this amazing result because they were able to find a circuit, a fourth-order circuit that reproduced the dynamics, the linear dynamics of an action of a neuronal axon membrane. This is the circuit representation. Okay, you see it has two biological memristors, right? The sodium, which is a second-order biological memristor, and the potassium, which is a first-order biological memristor. And then there is, of course, the capacitance. Okay, so the sodium has two states, so N, M, and H. So there are two state variables for the sodium, one for the potassium N, and Vm is the voltage across the capacitance. So there are four states, and therefore it's a very complex model. These are some auxiliary voltage-controlled functions that are used in the potassium and sodium equations. And this is the DC characteristic. It has a similar shape as the characteristic of a junction diode. Okay, it has a rectifying characteristic. Of course, one has to, in order to apply the theory, has to derive the DC characteristic. The small signal model, in this case, one can consider, typically you should consider, because it's a net current entering the neuron, so you should consider the local impedance, but you can also evaluate it from the local admittance, but then you have to look at the numerator for the pole. For the poles of the impedance are the zeros of the admittance. And one can then study, the evolution of the zeros of the admittance to understand when there is instability, right? When the zeros enter the right half plane, right? So, for example, sweeping the DC current of the synaptic current, right? One can immediately see that in this region, of course, it's unstable, right? And then there is a region where the real part of the admittance is negative. It includes the region of instability, but also these two regions, edge of chaos 1 and edge of chaos 2, okay? So, in fact, going in more into the details, we have a region of instability, so right half plane poles, right? Then we have region, of course, these are edge of chaos domains because we said that the real part of the admittance is negative and all the zeros are in the left half plane. And then there is the other two, of course, that are locally passive region, okay? And one can identify the bifurcations. I mean, if studying the model, one can show that there are two bifurcations, the edge between edge of chaos and instability, okay? So the first one is the supercritical off bifurcation. So supercritical means there is the birth of a stable limit cycle, oscillations, the stable action potential train. And there is another one, which is fundamental as well for the all-too-known phenomenon, is called subcritical, which actually means that there is the birth of an unstable cycle, okay? And this is the bifurcation diagram, in fact. We can go through the details. These are stable operating points, okay? Initially, we sweep the current from 180 microampere down to 0, okay? Initially, we have stable operating points, so the neuron is sitting in a quiescent state. Let's see what happens at 155 microampere. So we are, before any bifurcation can happen, of course, the neuron is silent, okay? These are time waveforms. This is the phase portrait, or better, the projection of the phase portrait on a two-dimensional plane. Then now we have a supercritical bifurcation. So the birth of the action potential train, okay? So these are in black. We have maxima of the oscillations in magenta the minima, and then we have the unstable operating points. And okay, now so we see that now the stable oscillation just started, okay? And actually, we know that this is a supercritical of bifurcation, so we have almost sinusoidal oscillation starting. You know, they don't look like action potential. They will look as action potential later on as the current will be decreased further. So if we move at 60 microampere, now the limit cycle has grown, right? So we have stable oscillations, and here is this is the stable oscillation. So if you look at the time waveforms, now they look really as action potential. We don't have to go to the details here. And now we come to the second bifurcation. So this is the subcritical bifurcation here. At this point, there is the birth of an unstable. These are the maxima and minima of an unstable cycle, okay? So if we look at just at the bifurcation, now we enter a region of bistability. So there is still the stable cycle, but you see now Qn, the operating point, has become stable now. So if we zoom in here, we have now the operating point has returned to be stable, but we have an unstable cycle around it, just born. And this happens actually at the other edge of the edge of chaos domain 1, which is the other edge of chaos domain. And if we move now in this bistability regime, you see that the unstable cycle grows, you see, while the stable one remains almost the same. This is a bistability regime. So either we go to the, depending on the initial condition, either we have the action potential train or the quiescent point, okay? And we are actually able also to detect the unstable cycle, the unstable solution. See, this is, for a while we are in the unstable solution, then we move either to the cycle, the larger cycle, the stable one, or, and this is the zoom of the unstable solution, or we are in the, again, for a while in the unstable solution, and then we move to the quiescent point. So this is the bistability regime. And then finally, you see that we are now, the two cycles are approaching. At 7, they're almost together. And now look, this is the global bifurcation. They're going to get together. And then this is the so-called saddle node limit cycle bifurcation. They're actually one on top of the other. And we have basically the collision and then the disappearance. So actually, this is the all-to-known phenomenon. Because from this point to the other point, now the neuron returns to the quiescent point. So this is the famous all-to-known phenomenon. But it takes a lot of time. It's like there is a ghost trajectory here. So if you start now the initial condition far away from the region where the coalescence and disappearance, the saddle node bifurcation appeared, you basically spend a lot of time in this ghost region where the limit cycles are not anymore there, but still the neuron revolves a lot of time around it. And so basically this resolves all-to-known phenomena because the solution to Galvani's enigma is actually the mechanism responsible for the annihilation preceded by gentle coalescence between a stable action potential train and an unstable periodic signal. Both of them actually have been generated at the edge of chaos. Okay? And so this is actually a portrait that Leon Chua introduced to explain this phenomena. Basically, you have in the bistability regime, right? You have a stable operating point, and you have a stable periodic orbit. Inside, you have a stable operating point, and you have the unstable periodic orbit. So this is just proceeding. Finally, you have a saddle node bifurcation, and then again the question. So this is the all-to-known phenomenon. Just since we probably don't have so much time, I just give you 2 more slides. So this is actually, if you want to have more news about the details about the study of this, we did some study explaining the fundamental role of the sodium ion channel in the Ascoli and Ascoli neuron model. But most importantly, actually the result, they are still unpublished, so we cannot provide all the details, but I can show you perhaps, I don't know how much time I have.
Yeah, I mean, this goes all against the discussion.
Okay, so basically, maybe I will give you, so basically just to show you that we have this memristor and is able to amplify the small signal fluctuations in energy. So you can see that this is a demonstration that the enamel memristor can behave as a local energy source. We did the demonstration of the local activity principle, demonstrating that basically biasing in a certain point and then applying a small signal, actually the local energy is going to get negative and negative more and more on time. And we use this memristor actually also to reproduce other complex phenomena in biology through simpler circuits than the biological equivalents. So we have a few papers if you're interested about Smale paradox resolution, about Turing instability and symmetry breaking phenomena. But most importantly for this work, we are able to actually reproduce the bifurcation of the Ascoli and Ascoli neuron, which is a 4th order model, using just a 3-element second-order circuit. And this is the bifurcation diagram showing you supercritical, subcritical, and full cycle, the global bifurcation. So this is the major result in our opinion. Thank you. Thank you.
Okay, thanks, Alon. So one or two questions are still possible. So, questions from the audience? Yeah, so then I would have one question to this first, first audio, what you just mentioned. If you go, let's go back to the slides.
This one?
No, go back to a few slides where you. No.
This one?
Then I'm.
Here?
Oh, okay, that was the topic. So what is exactly demonstrated here for the first time? So.
Yeah. Basically here, what we did is we demonstrated that the NAMLab memristor can act, this niobium oxide memristor can act as a local energy source, in the sense that we first drove the memristor with a bias current of, I think, 3.1 milliampere in the point P, okay, of the characteristic, which is a point at negative differential resistance. And we apply then a small signal current, in this case a small signal sine wave, delta IS, on top of the bias point. As you can see, the black, little black segment is basically this, the trajectory that after of the small signal response to the small signal perturbation. And then we actually multiplied, of course, voltage and current, and integrated it, and we observed this behavior for the local net energy. Of course, the device is globally passive, because, of course, in this kind of computation, we don't add the energy that is used to bias the device. But in terms of the small signal, is able to the local, basically, it's delivering energy to the outside.
Okay, but isn't this the case always for negative differential resistance? So I would expect it for any type of negative differential resistance. So
for any negative differential resistance, you can observe this.
Okay.
Because this is actually for if the device has a negative differential resistance, it is locally active. And this is you can also do the math because it becomes a linear system. So this, in fact, we have the theoretical prediction and compared to the simulation itself. So.
Okay.
Further questions from the audience?
Yeah, I've got a question. My name is Timo Oster from TU Darmstadt. It's really two questions. The first one is, in practice, how hard do you think would it be to hit the right biasing current for each memristor, maybe in an array? So the memristors might differ. Do you have an idea how hard this could be, or would it be not that critical from a standpoint of device-to-device variation?
Yeah, okay, from a perspective of demonstration, as I said earlier, even reproducing this bifurcation diagram experimentally is now still underway. So this is, in our opinion, is very nice theoretical work, but the issue of experimental demonstration is not an easy task, because entering in this bistability regime, where typically it's not so large, of course one can tune the parameters to make it larger. This is a very robust, using models that have been used. We have demonstrated their accuracy for over the years, but using the models, you can actually make the window of bistability larger. But that's probably one of the reasons why experimentalists have not discovered this. You can have actually three, depending on the capacitance regime, you can have different bifurcation diagrams. And entering the regime where the bifurcation diagram of the Hodgkin and Ascoli is observed is first already computationally intensive. I imagine it's even harder with experiments. And also, it's actually hard. It's known to be very hard to detect subcritical, because you have to detect the unstable oscillation.
Yeah.
Of course, you need to change the initial condition of your capacitance, and then you're able to go either to the limit cycle or to the quiescent point. But this is not an easy task. Yes.
Yeah. Okay.
So
my
when
second
you talk about arrays, okay, it gets of course more complicated.
Yeah. So this is also where my second question would go. Would you think it would be useful to optimize the devices for this aspect?
Yeah, I think so. I mean, the reason why we are showing this, maybe this can attract the interest from people that are using neuristors for their computation, because typically we heard, of course, there is the well-established CMOS technology, and people are using, typically leaking integrate and fire and using CMOS devices, but perhaps this is a very simple circuit that perhaps can be interesting to develop and to experience.
Yeah, thank you very much.
Okay, so let's finally thank Aaron and move on to the next presentation.